first, I will introduce you to the basics of this course. What do we mean by geochemical cycles, and maybe a few words about the main actors of biomineralization on Earth now. So first, what are geochemical cycles? Actually, what we mean by geochemical cycles is just the exchanges of matter, the fluxes of matter between reservoirs we define on the Earth. So what is a reservoir? It's in geochemistry, we make a box, you know, that's why we call box models. And it's a box, for instance, so it has not to be a well-defined physical system. For instance, here I have the atmosphere plus hydrosphere, the air plus the ocean. And in box, you have constituents, like for instance, carbon, which is in the form of CO2 in the atmosphere. And what we do, we try to calculate, to define processes and to calculate fluxes between these boxes. That's the basics of modeling geochemical models. For instance, here you see the atmosphere and hydrosphere with the CO2 and the biomass. So all the living organisms, right? So you see it's really a box, it's not a physical system. You have the amounts of, for instance, equivalent CO2 in it. So of course in the atmosphere it's CO2, carbonate ions and so on. In the biomass it's organic matter. And we have processes, for instance you have the photosynthesis here in green, the CO2 assimilation. And you have kinetic equation, so it's basic chemical kinetics between these boxes. So you have the constituent I, which is, for instance, exchanged between boxes with a rate. For instance, here its atmosphere is depleted by photosynthesis with a rate of that photosynthetic process. And that's the way, and I will show results of this model, that's the way we try to model the events that occur in the biosphere and at the surface of the Earth more generally. So in this talk, I will focus mostly on the carbon cycle. So sorry for those who work on phosphate biomineralization, for instance. But what I want to say is that, of course, the carbon cycle is very important. But for instance, if you work on phosphorus cycle, which is as important, it will be phosphate biomineralization will be very important as well. But here, of course, I will concentrate on biomineralization, more focused on the carbon cycle. And actually, this is a cycle, you see, for some magical reason. We can come back later on. The system is stationary, and the rate of photosynthesis is exactly compensated by the rate of respiration. Return of CO2. Actually, it's not exactly compensated because, as you may know, when you have a soil or a forest or whatever, you produce some organic matter and some of it goes in the soil, and eventually some of it is transported by the rivers, brought to the ocean, brought to the deep sediments and taken out of the system, right? So you have what it means. This is very small, right? This is 1% of that, but it means that the green arrow is slightly, the rate constant of the green arrow is larger slightly than this rate constant. So you have slightly more photosynthesis and respiration plus combustion. And if you have this, so this is not a cycle, right? And we talk about cycles for geochemical, for historical reasons, but these are not cycles. Here you see there is a leakage, but you see if you have the leakage, what will happen is that you eventually will deplete all the CO2 from the system, right? So there must be some return mechanism, so we must go back into a cycle. And actually, we really need to have a geologically active planet to have the return of carbon, and magmatism, metamorphism all contribute to that. I wrote volcanoes here. They are probably the most evident contributors, but all the geological activity of the planet. So we need an active, geologically active planet to sustain a carbon cycle, definitely, to return the CO2. But you see here, you have another problem. So these numbers, of course, we can talk about the precision on these numbers. They are not, we can discuss about that, but this is, you see here, there is an unbalance, obvious unbalance. In that case, if you have this, if volcanoes outgas all CO2 and you have not enough compensating mechanism, you end up with a planet which is full of CO2 in the atmosphere, and like Venus, for instance. And of course, then you have a very different planet. So here on Earth, we have to close that system. We have to have this 0.8 compensated by a 0.4 and another 0.4. And this is where biomineralization comes in play, because actually on Earth, on the present-day Earth, the return flux, this missing 0.4 gigatons of carbon per year, is actually the actor of this flux is biomineralization in the present-day Earth. So you see, obviously, we already have the impact of biomineralization on the biogeochemical cycles. And this comes from the fact that the pumping of CO2 from the atmosphere to make carbonate and export them out of the system to the interior of the Earth is in great majority, more than 95 or 96%, the numbers are difficult to tell, is in great majority associated to biomineralization. You have abiotic formation of carbonates on Earth, of course, but the great majority in terms of flux is performed by living organisms. So that's the basis. Just to be complete on the carbon cycle, of course, the carbon cycle now is fully unbalanced because we take that slowly accumulating reservoir as a fossil fuel and we return it. It's just to give you the number. Actually, now it's more like 30 or 32. And so it's interesting to compare the geologic action of man on the carbon cycle with other geologic actions. But in this talk, since I don't have time, I will not speak very much about the destabilization induced by this, especially on these arrows, which is Anders Maybaum said a few things about corals evolution in a global changing world, but I will not talk too much about that. So then the second part of the introduction is to what are the main actors of biomineralization on Earth. So coming back to the, I will start with the carbonation because I started with the carbon cycle. So I started with this number. So I will start with the formation of CaCO3. And you have this number, 0.4 gigatons of CO2 per year. So I take numbers which you should not take as perfect numbers, and everything can be discussed. But as a matter of fact, on the Earth, the main actors for biomineralization of CaCO3 are unicellular photosynthetic eukaryotes, such as the coccolithophorites, and they are responsible for about half of the flux. Not meaning what they produce in the ocean, which is much more, we will see that later, but what they export, what is a contribution to the export to the solid Earth. Then the second actors are the forams. We had a talk about that in the school. And they are very, very important as well. And the third, so I convert this into moles of CaCO3 because it will be interesting to compare with other biomineralization using moles. Of course, I can use the CO2 equivalent for the carbon, but if I have something else than CaCO3, I will have to use moles. And the third ones are the corals, which are, you know, all the bivalves, the gastropods, shells, and so on. They are very little, right? It's less than a few percent of these contributions. But surprisingly, the animals, the corals animals, because they build a large amount of carbonates, they contribute to something equivalent. Of course, we also have other, as I said, other calcifying organisms, and that's a view of the present-day Earth. what was going on a few million years or a few hundred of million years ago, nobody knows. Nobody really knows, actually. What is the role of bacteria, for instance, in this calcification process? And what I like very much in this world of biomineralization is that you always have surprises, so you don't know how to take them. But for instance, you see, if you do you can have the overlooked contribution of fish, for instance, the fish guts, right? So that means that, of course, I give you numbers with main biomineralizing systems, but it's a scientific field where you can have blooms of something else and reconsideration. So that's quite open, I think. So continuing to the major actor. Actually, the major actor of biomineralization on Earth is not a calcifying organism, if we take in terms of tonnage, of mole numbers. It's the diatoms. I'm sorry, I did not write. These are the diatoms. And the diatoms, they really contribute to, so if you still have the mole numbers in the carbon cycle, they contribute really to major quantities of production in the full ocean. And it's interesting that they must somewhat play a role in the carbon cycle. We will talk about that later, but it's SiO2, it's not a carbon-bearing system. So that's interesting. And the SiO2, we should never forget that the SiO2, the major contributors of biomineralizations are the plants, actually. And they have a comparable amount of SiO2 production as diatoms, but they are on land. So the contribution to the export, which is here the number under parentheses, is really unknown. It's a matter of erosion and transfer cycles. So people are working on that using silicon isotopes, but it's difficult. And finally, I will go a little bit on the fringe of biomineralization in the sense we understand biomineralization in this school. It's actually, but we will talk a little bit about that, the production of lignified tissues, which chemically are very enriched in carbon, most often. At some point could be considered as as maybe the most important biomineralization if we want to talk about that like that. It's not a mineral, right, for a mineralogist, but it's a solid, it's a natural solid, so it's somewhat a mineral anyway. So now I come, now that I am done with this introduction, I'm going to go through the lecture. So in comparison with what Thibaut may have shown you on Monday morning, I decided not to talk about these global changes issues for sake of time, but maybe I will go fast, so I don't know. But anyway, I prefer to try to concentrate on this. So let's start with this effect on the carbon cycle, how to discuss that. So how does it work on Earth? That first we need to understand how it works. You remember in the carbon cycle, the biosphere is transferring CO2 from the atmosphere to the deep Earth. So it's really a CO2 pump at the scale of the geochemical cycle of carbon. How does it work? This reaction is so-called Berner reaction. Actually, it was known already in the 19th century, before we knew any about atoms. People were considering that because it's a basis acid neutralization reaction, which is the most obvious acido-basic reaction of natural systems. So it works in two steps, meaning that on land, on the continental crust, you have dissolution of the silicate minerals forming the rock. And actually, water itself on silicate does not do anything. It's acidified water. CO2 is an acid. And so the acidification of water by CO2 results in the liberation of HCO3 minus, the bicarbonate, the hydrogenocarbonate ion. And so you see you have trapped CO2 in the process. CO2 was in the atmosphere, it was dissolved, and it's trapped in the process. Actually, most of this alteration, you have to realize, is also probably done by biology in that sense that it's the PCO2, the pressure of CO2 induced by root systems at the contact of rocks in the alteration, which is a major contributor to that. And then, when you have this system transported by the rivers and coming to the oceans, in the ocean, there is the so-called supersaturation and the precipitation of CaCO3, which occurs, as we said, almost only in living organisms. So that's the way the Earth, in the present-day Earth, is pumping the CO2. It's one of the ways the Earth is pumping the CO2, and somewhat regulating also the CO2 on the long time scale. Because, for instance, if CO2 increase, I make a small toy model just to explain you, but if CO2 increases, temperature increases, and presumably these processes have faster rates and attempt to decrease the CO2, a kind of Le Chatelier principle, which is not so easy to verify at the scale of the Earth, but it's probably working anyway. So, just looking at the, I'm sorry, this slide is a little bit complicated, but just to illustrate one point, which is very important in the biomineralization, and I switched to moles here. So if you look at the ocean, you have production of CaCO3, so this is a number of moles in the surface ocean, mostly, and mostly close to the coasts, but also in full waters. And this production is exported to the bottom. And here you have the very famous phenomenon that you may know, that if the ocean is too deep, the carbonates are redissolved. That's the so-called compensation depth of carbonates and so on. So actually this 74 roughly corresponds to the depth of the ocean, which is not too large, so as to avoid the redissolution of the carbonates, right? So that's why you have this strong reduction. And the export to solid Earth is given here because you again have a utilization of CaCO3 in this deep system. So it's just to understand that. And now we can ask the question. We have this cycle. We know that in the present day Earth, the biomineralization is really closing the cycle. Is it really doing something if we let the system go and presumably, maybe in some places it happens like that, by the way, if there is no organism to make the CaCO3, the saturation will increase a little bit and the CaCO3 will be done anyway. So does it really matter that we have organisms making the carbonates? Is it really important? So I think I will try to convince you that it is very important, and that it is very important to understand even the details of biomineralization mechanisms to understand the cycle. And this will be true for that. This would be true for other parts of the other geochemical cycles as well. To explain that, it holds from the thermodynamics and kinetics of that reaction. We have a rate constant, and obviously if we change the rate constant, there is something which could happen. But to be more precise, we need to do the thermodynamics and the kinetics of that to see whether it's different when we have biomineralization or whether we have abiotic precipitation, and to see whether it has an impact on the carbon cycle. So I just make this small warning here because we are in a framework of solution chemistry, precipitation of minerals in fluids. And we don't know, I like to quote that Weiner and Dove, but other people have said that that's our paradigm, right? We have at some point a saturated solution and we make at some place the minerals. But what we see here, I think he was speaking about the spicules of urchins, I think. What we see is that there's colloids or whatever, that are transferred, and so maybe the paradigm can be challenged. But my point is that at some point you still have the seawater, right? At some point, and at some point you have a fluid, and so at some point you have to precipitate a solid from the seawater. So whether or not this is not that intervenes in the detailed shell mechanism formation or whatever, that's a different issue. So to me, it's really legit. Although we have these concerns and we are aware of that, and this is a challenge for thermodynamics, this is really consistent to talk in terms of thermodynamics and kinetics of nucleation and growth of biominerals in a fluid, as we had the first lecture by Dennis Gebauer on Monday. And so I tried to use the same notation as he used in his course. So we have this so-called saturation index, SI, which is simply the ratio of the ionic products divided by the product at equilibrium. And as he showed on Monday, to make a biomineral, or to make that biomineral, for instance, you need to at least it has to be thermodynamically possible first. So the SI has to be more than 1. That's the basis. And what he showed is that it even needs to be much more than that, because you need to overcome barriers. So I would like to talk a little bit about that in that perspective. And just to let you notice that, of course, we can analyze that very well. We have thermodynamic measurements. We know that very well. So we can measure, and this has been realized actually not so long ago, I would say, in the 50s. It has been realized that the saturation index of the ocean is more than 1. So actually, if we did not have nucleation and growth barriers, all the ocean should be precipitating carbonates everywhere, right? It does not. It does not, because the critical index, I wrote a critical index for calcite. We could discuss to infinite what is this value, but well, it's much more than that. But it has very important implications, because when you have a carbonate in the ocean is not precipitating spontaneously calcite because ocean is below the critical index. It's very clear. But once you have made a carbonate in it, since the critical index of the ocean is more than 1, the carbonates do not dissolve back. That's very important. And of course, in a changing global CO2 changing world, if you increase the CO2 pressure in the atmosphere, you decrease the SI. And projections tell you that the SI of aragonite, for instance, could be less than 1 in 2100, in year 2100. So it could be a very serious, well, I said I was not going to talk about global change anyway. So that's the framework. And what the message I would like to tell here is that so this is a scheme which has no pretension of giving any mechanism. So please, if you work on detailed mechanism, do not look at that, but look at it anyway, so that I can explain that. At the beginning, you have seawater. Which is with this saturation index 5, which is not going to let you make the carbonates. And at some point, you have to have vesicles of seawater, which are internalized and strongly modified. So the fluid has then a small comparison with seawater. It's strongly changed by ion pumps and membranes and so on. But what is really important is that here you have the carbonate precipitation, so maybe not the definitive calcite, maybe a colloid, and then it will be exported, as Weiner said, but at least you have here the event of solid formation. And this thing is giving you a local thermodynamics somewhere, maybe very difficult to get, which gives you an effective saturation index provided by this organism. And you have to realize that the saturation index of 5 for the ocean is really the product. It's not to be reductionist to say that, it's really true. It's really the product of the sum, rather than the product, of all these contributions of all these calcifying organisms, leading to that actual saturation index from that effective mechanism. So to me, that's a link which is very important. And so it's very important now. It's not only a detail, I think, not only a problem of rate in the carbon cycle, is that if you look at how these geochemical models work, most of them now are sophisticated and they have components, and they try to take into account the fact that the carbonates are not in equilibrium with the PCO2 because of that supersaturation I noticed. And the pressure of CO2, the most immediate pressure of CO2 you calculate above the ocean in these box models is related to the saturation index directly. So just imagine for some reason you have an ecological shift and you completely change the effective saturation index of carbonate formation, you will change the pressure of CO2 in the air. And that's really something, it's not reductionist to say that, it's true. And it's even so true that if you think in terms of this SI, for instance, you see obviously that the ecological balance between aragonite and calcite, for instance, in biomineralization, is going to have a direct effect on this geochemical model, direct. If you change the proportions of aragonite and calcite forming organisms, you will change the global system. And also more details, as I said. If the calcite are magnesian, it will change. And even this local saturation index, when you make the calcite or when you make the aragonite, are very important. So to me, that's a very important link between the biomineralization and the carbon cycle. And you know, when we are in mineralogy, for instance, we find it normal to calculate all the rate constants of dissolution of minerals for calculating the CO2 pumping, for instance, by the alteration. Now, in ecology, in biogeochemical models of the ocean, I think one should really go down to the local ecosystem scale to calculate these effective parameters, like we do it for individual minerals in rocks. So I think it's an important eco-physiological program for. That's why we need to understand these mechanisms, I think. So coming to the point, you have this, to summarize the point, you have this vesicular system. You have some unknown concentration in it. So I think that's still, although there are data, of course, but that's still a challenge for, I think, biogeochemistry to measure that in real cells, in real environments, in real vesicles. I think it's not easy. And you see what happens. You have the CO2 produced and the CO3 to minus. And by the way, you see that the precipitation of carbonates is, as I showed on the transparency, is releasing CO2, right? So globally, the carbonates are sequestrating the Earth's CO2, but the event of biomineralization is releasing CO2, which is another way to say that CO2 increasing in a global changing world, in an acidifying ocean, is detrimental to biomineralization. It's interesting now that we have the present-day Earth. It's interesting to look at what happened in the ancient Earth. So just look at this violet curve, which represents the pressure of CO2 as a function of time before present. This is by no means a measurement. Right? It's an unconstrained model, I would say. So don't take this as a... There are some constraints, but we don't know that curve. That would be an ultimate goal for geochemistry, to reconstruct the pressure of CO2 curve in the past. I just want to mention that, okay, we have this carbon cycle, as I said. I showed you that the pressure of CO2 is related to the biomineralization in a very efficient way. So of course it's legitimate to ask the question, what was the biomineralization doing here or here this peak. But anyway,
why you have this kind of, in the Precambrian, why you have this kind of...
This, well, we can talk later about that.
No.
This is a box model. Here, you know, it's not the, here, telling you the truth is here, you know, it's just before the Cambrian explosion in that case. And they assumed, I'm answering you the question, but I think it's really unconstrained. When you make these box models work, you know, you have important glaciations at this point, global. Even it's quasi the so-called snowball Earth, right? And so you have, after this glaciation, when you have made all the grinding of rocks and so on, you have a very strong delivery of nutriments to the ocean. So you have a big destabilization in both cases of the carbon cycle. So when you let this box model work, you get big peak. But anyway, I don't want us to focus on that. What I just want to say is that in some respect, this is related to biomineralization in a complex, very complex manner. And especially in the Precambrian, then it's exclusively related to prokaryotic or unicellular eukaryotic and prokaryotic biomineralization. So it's interesting. This is exactly why this is exactly why I think it's very important in this ancient, if I talk about very ancient Earth, for instance, it would be very important to have an idea of this effective saturation index in such systems, to build in a geochemical model and to make this. And it's very legitimate, I think, to study, as many people in the room do here, or several people in the room do here, to study this system in actual Earth, to try to understand, I would say, globally this saturation index. It's even more important, from my point of view, to have discoveries of new biomineralization styles, such as that one done by Karim and his group. Because, of course, you imagine that the effective saturation index, I simplified the picture, but the effective saturation index in cyanobacteria doing this thing extracellularly on biofilms, and the effective saturation index protected within a cell. If this thing were, for instance, generalized, it changes maybe your model of CO2 pressure if you have data. So actually, in Karim, they suggest that it's at least, does not mean that it's ancient, but at least looking at phylogenetic trees, it suggests some ancient character of such a system. So maybe, as we had in Christopher's talk, maybe a lot, all of them could do it, but and lost it. I don't know, but anyway, it's very interesting that, and to me, discovering a new mechanism like that and trying then to diffuse to the community of geochemical models so that at least one number will come out of this very detailed mechanistic studies is very important. And I'm provocative here. But if you can get that in the real actual present day system, at least you can discuss scientifically what may have been going on earlier. Another very important point I want to point is the connection between the carbonate biomineralization and the photosynthesis. Actually, we heard Anders Maybaum saying us that the zooxanthers had not really impact on the CaCO3 formation in corals, and you have deep sea corals making the CaCO3 quite well. But anyway, if you look at the main biomineralizers we examined, there is always some connection with photosynthesis, right? It's not easy connection, but there is some connection, and it's understandable because in doing that process, actually the enzymes, usually the Rubisco, for instance, usually they really need that, right? They do not use that directly. They really need that. And so the point is that there are interesting connections. And just to illustrate you, I have no solution, no clue about that. But if you look at the organic production of organic carbon, this is the total so-called primary production, the total photosynthesis, C-org, organic carbon, and the CaCO3. These are really decoupled, right? You have the diatoms, you have plenty of non-biomineralizing organisms. This is fully decoupled. But it's interesting, and I tell you I have no solution, but when you look at the export and what eventually reaches the bottom of the ocean and which is transferred to the Earth, you see that these numbers have come to parity, and I think it's very interesting to understand. So there is a connection between the biomineralization of CaCO3 and the primary production that you can summarize like that. And to me, a major question, because of course all this CO2, which is used for making the new biomass, is not going to intervene, for instance, in the relation between PCO2 and omega I showed you. So this coupling is the other main point for in biogeochemical models to assess the impact of biomineralization on the global cycles. And I really think we need, once again, to discover mechanisms that describe the coupling of the CO2 release by the CaCO3 production and the photosynthesis in that cell, or maybe in other cells in the ecosystem, I don't know. So we need a trophic flux monitoring of that CO2. Actually, if you look at so the carbonic anhydrase, I mentioned it because it's the fundamental system which can equilibrate this, and so it can strongly affect the production of biomass at the scale of a cell, definitely. And this, what Anders Bebob called the vital effect on oxygen isotopes, for instance. One illustration of this vital effect is, of course, if you take part of CO2 for metabolic reactions, and that could be seen in the biomineralization record, and it's interesting to have this look at the problem. Now I want to return to this very model, not unconstrained model curve, but it's at least in one part, this curve of pressure of CO2 as a function of time, present is here, 60 million, early Cenozoic is here. You have the pressure of CO2 which is decreasing in the box models. I can show you maybe some hypothesis for that, and I will give you one related to biomineralization soon. But you see here the temperature, of course, in that case is well correlated to the PCO2 pressure. And this is not an unconstrained model. This is a truth. This is shown by the fact because, for instance, 50 million years ago, you have no ice sheets, polar ice sheets on Earth. Then the Antarctic ice sheet is coming, and then the Greenland ice sheet is coming. And you have a cooling of the average temperature of the Earth by about 12 degrees on average for, say, 40 million years. So it's well constrained by at least the geological record. And of course, you imagine that people doing box models spend most of their time to understand that global cooling. By the way, this global cooling has no relationship with the present day warming, right? We are not talking about the same time scales. So this global cooling, it's interesting to note that one of the hypotheses, which begins to be implemented in the box models, but it's very poorly constrained, regards the fact that I mentioned to you that, okay, we have the carbonation, and I told you that the main biomineralizing organisms at the scale of the Earth are the diatoms, which are making the SiO2. And this is a relatively ecological recent transition. And nobody has very precise data about that, but the ecological success, major ecological success of diatoms is not completely decoupled from this time scale of Earth cooling I showed you. And maybe a possibility, actually in models there are two possibilities regarding the diatoms, which could, and the details of biomineralization in the diatoms. One is that maybe you switch from a carbonate forming exporting organic matter. You remember the carbon cycle, right? There is export of organic matter. But if you change, for instance, the organism doing the primary production in the earth from carbonate producing to silica producing, you have less carbonate formation. And then you have less CO2, instantaneous CO2 release in the system. But the main thing, this does not work very well in box models. But what works very well in box model is the fact that the diatoms are often large cells for some reason, I don't know, and often very good exporters. Although their silica shell is dissolving, they export very well. So if you increase this rate, maybe you can cool the earth. The mainstream hypothesis for this cooling is not that, right? It's a tectonic hypothesis, but it could be. Biomineralization could be this interesting thing. One thing I'm particularly interested in is a really unknown contribution to the carbon cycle. I just show you two images. Is the possibilities that inside the earth, so not related to photosynthesis a lot, you make carbonates, biocarbonates as well. And that's work that we do a lot in the context of CO2 sequestration, because here you inject CO2, and if part of it is transformed into CaCO3, it's interesting. I just wanted to show this image to Juanma, because these subsurface microorganisms, of course, they make carbonates which look fully abiotic, right? Fully, as you showed, the same. And the only thing, we did this experiment in groundwater, reconstituted groundwater for ions. We did not put the silica, so probably, because we have aragonite, vaterite, and calcite in this thing. So it's I think this is a terra incognita. What is this part of the carbon? Is it negligible, or do we know? I don't know. So now I'm going to switch to the second part, which is the oxygen. And the oxygen, to explain you what's going on with, again, the connection between the geochemical models and these box models and the oxygen, I come back to the carbon cycle. Because if you look at the carbon cycle, you remember at the very beginning, I told you this arrow, this rate, is faster slightly by a few per mil, is faster than this rate, because there is this escape of organic matter which cannot be respired, which has to leave the system. So there is an excess of and if you look at these two arrows, if I write the reactions, so I just symbolize the reaction of the photosynthesis, like CO2 making the biomass, which is as you know, very precisely CH2O, right? This is the box model in geochemistry. And but anyway, well, actually, if you multiply by 6, you get the glucose, so it's not too bad. But we know. Anyway, this is faster than this. So what you see immediately is that the difference between these two numbers is that. So the consequence, obviously, is that you have some oxygen which is left. Some oxygen which is left because this organic matter has gone very fast, deep in the earth, and has there was nobody to respire it. And so this oxygen is left there. So you have a continuous accumulation of 10 to the 13 moles of oxygen per year. So if you calculate what's going on. For instance, we could do the calculation right now, but if I think there are 10 to the 20 moles of O2 in the atmosphere about. So you see that in 10 million years, oxygen content in the air should double, right? And the oxygen is probably one of the most regulated system. So of course, there are controls. This is the history of Earth's oxygen. Much better constrained than the PO2 curve. You see, you have proxies everywhere, but not so well constrained anyway. 50% of geochemists are now working on that, seeing peaks and. But anyway, what is for the sake of what I'm saying now is this region here, which is the present day, the last 500 million years of the Earth. And at this scale, you see very well that the oxygen is very far from doubling every 10 million years. It's very, very well constrained. So that means that something must, because this is a universal mechanism, there is no speculation about that. So something must regulate O2. And something which is not in the surface system. So that's in. This is a mystery, I think. One has to add something in the box model to regulate oxygen. And one interesting thing which was proposed by Holland was the changing the chemical composition of the biomass could somewhat regulate the oxygen. It's interesting because actually you see in a huge effort in a box model we changed the composition of the biomass to the so-called Redfield ratio. The carbon over nitrogen and carbon phosphorus are put to some average, which looks like an average cell. And if you remineralize, by the way, this is mineralization for a geochemist, not for mineralogists, but if you remineralize, that means you make the CO2 again, the biomass. You see, for instance, for 1 carbon in the biomass, you pump 1.2 O2 when it descends in the ocean. And you see, for instance, if you take a piece of wood and put it at the bottom of the ocean, the remineralization reaction will look more like that, right? Because wood is carbon, for instance. So meaning, and so you have less O2 pumped, and so you can change. You see, if you change the chemical composition of the biomass, you can change the oxygen cycle. But so that is a very serious possibility. But that's a serious possibility to explain maybe some transitions. That maybe, for instance, in the Carboniferous, you have the lignified tissues maybe coming on the continents, and you change completely the style of carbon remineralization, and you can change. But of course, to regulate continuously the oxygen is not going to work. And when you turn the box models in all directions, the only system you can find to regulate this continuously coming oxygen is the oxidation of iron 2, which is continuously provided by the deep earth, because the deep earth is a reduced medium. There is a metallic core, and the deep earth is on the so-called FeO, Fe oxygen fugacity buffer. So most of the iron which is coming out from the earth by the plate tectonics is iron 2. And when you look at what is reinjected in the subduction zones, it's what has happened to first order is that you had a pumping of oxygen. And when you make a box model, you find it matches quite well the photosynthesis respiration unbalance. It's the purpose of this paper, but it's really very impressive. It matches quite well. And so the question is, so you see the plate tectonics is really essential to regulate that oxygen biospheric component, because you pump oxygen by this process. And of course the question comes now, how does it change over the geological history? What are the abiotic rates? What are the biologic rates? And that's where the biomineralization of iron is going to come in play, because when you oxidize the iron 2, which under anoxic condition is soluble, or which is in the solid, to iron 3, you make an insoluble mineral. Iron 3 is insoluble. And so if it's done by an organism, you have performed, maybe not controlled, but real biomineralization. An interesting thing, I'm very interested in it right now, is the fact that the rate of this convection, of this reaction, you can try to put in a box model, is very dependent on temperature, as any chemical reaction. And so the question is, on that cycle, what is the part of the highest temperature points in the amount of this reaction? And that's a really fascinating, you know, you have biology there. It's really a fascinating issue, because if you increase the temperature, the rate of conversion is going to increase very fast, doubled every 5 or 6 degrees. But of course the biomass, because it's also proportional to the actors, right, to the biomass, is going to decrease and come to 0 at 120 degrees maybe. So it's really interesting to establish that point. And I put this here to explain. You have the iron 2+, which is oxidized to some insoluble, so the FeOH3, it's insoluble iron 3+ phase. And you have a lot of possibilities. You can regulate the oxygen. You can make chemiolithoautotrophic production of biomass. You can make hydrogen, and then later on use that hydrogen to fuel biomass again. So it's a really fascinating system to understand that, and I think maybe in the biominerals that you may form, you have maybe the answer of the process. I just put that image for Puri, because this is these shrimps which are living close to the hydrothermal vents. And a long time ago with Alexandre Lotter, we looked at and with Magalys Binden, we looked at bacteria from the gill chamber of the Rimicaris. And at the time we did not pay attention, but this is ferrihydrite. And well, this really looks like an iron oxidizing system. So that's what we need, the rates of these processes, how often. At some point, if they were very important, we should put them in box models and try to see the highest temperatures. Coming back to the oxygen, you see that the most striking thing is the very low oxygen pressure in the past Earth. So there are peaks, there are things like that, there are controversies, but I'm telling you, it's very, very difficult to me, it's one of the most established results of geochemistry. Really, the past Earth, before 2 billion years ago, was really devoid of oxygen. There was maybe an incipient production of oxygen. And the big question then is that when you look at the sediments that were formed at the time in the ocean, they are actually, there is not a unique interpretation of this jaspilite, of this banded iron formation, of course, but I think from a mineralogical and petrological point of view, it's really consistent with iron 2 oxidation to iron 3. On one hand, it's normal, because if you have an Earth which has no oxygen, there is plenty of iron 2+ in the continental crust rocks, or even in the oceanic crust rocks. And so there is plenty of iron, There is a large amount of iron 2+ in the ocean, which is not the case now, right? Now the Fe2+ in the ocean is 10 to the -8 due to complexations with very specific molecules. But in the past, probably the iron 2+, since there was no oxygen, was very, very high. So you would expect a contribution of iron in the sediment. So in that sense, that's normal. But what you would not maybe expect is a contribution of iron 3. And the main minerals in this banded iron formation are magnetite, okay, which contains iron 2 and iron 3, but also hematite, for instance, which is pure iron 3. And so some people have said maybe it was deposited as iron 2 and then reoxidized in hydrothermal events later on. Maybe it's possible, but it's very difficult when you look at the structure. So there is some kind of problem here, and we are exactly at the same questions I just asked for the present-day Earth in hydrothermal systems. You have this iron 2, which has to be oxidized with iron 3. The difference is that here in this Earth, you have no oxygen, which is a very big difference with the present-day hydrothermal systems, for instance. So some people say, yes, there was some oxygen. There were the cyanobacteria. They were producing the oxygen, and it was somewhat captured immediately, and that made the banded iron formation. Other people say maybe there was no oxygen. Maybe you can do the photosynthesis, but do it without production of oxygen. Otherwise, you would have an oxygenated Earth, and maybe the anoxygenic photosynthetic are the explanation for the banded iron formations. And other people say, no, this could be purely abiotic, and you could just do it photochemically and make it. What is very interesting, if you look at the literature, sorry, I did not give the references here, I should have, in papers of Konauser, for instance, and is that what they do to have a scientific discussion about that, they take the rates of these reactions. For instance, the rate they give for anoxygenic photosynthesis, and they calculate the rates. From sedimentological point of view, they calculate rates of banded iron formation production. And what comes out of this literature, and it's not particularly wrong, I think, it's not very constrained, but is that the only candidate for making the banded iron formation is the anoxygenic photosynthesis. We could discuss in detail why. So that brings me to the fact that what can we do when we study biomineralization mechanism to contribute to that debate? One thing we can try to do, and of course it's not the absolute solution, is to measure rates of biomineralization in present-day existing systems doing the anoxygenic photosynthesis, for instance. And this is, so you can look in the biodiversity of the iron oxidizing bacteria. So you see there are a lot of, so the acidophilic iron oxidizing bacteria are very particular because in some way, although it's not always the case, but in some way they really use the oxygen to oxidize the iron 2+. But then you have also for instance, the nitrate dependent, who do not use directly oxygen, but who use nitrate. You may argue you need oxygen to make the nitrate, but that's another issue. And the phototrophic, who really need nobody. And this is work. So you have a lot of iron oxidizing system, which can be taken from the present day iron oxidizers. I put this image for you, François, because this is this iron oxidizing, as Karim said when you did your talk. You see this, and this is maybe a self-organized iron hydroxide system. So maybe not only aragonite silica, but maybe and as Karim suggested. And actually what Jennifer Mio, is, for instance, to measure rates. And you see, of course, when you do a detailed study of mechanism of biomineralization, it's very complicated because, for instance, here these are stick same images. I don't come into the detail, but just you have, in blue, you have the iron 2+, and in red, the iron 3+. And you see the rate, actually. You see the oxidation, and you have a rate constant. So in some conditions and so on. So how will it be transferred to the box model is another issue, but it's interesting. And you see it's very complicated because you have the bacteria which are oxidizing very, very fast, or relatively fast. And the extracellular system, apparently there are oxidizing agents transferred which are oxidizing. And the result of that is a rate of iron oxidation by these possible candidates for metabolic action in the early years. Another one, this one is the photosynthetic one. You see things like this, gradients of iron 2 and iron 3 along filaments on the bacteria. So in principle here, you have a flux. And so it's really interesting. And so my position is, of course, you are not going to transfer that rate constant to the box model like that. But the interdisciplinary discussion is very interesting when you try to make at least the geochemical model. And already we can make these images speak in terms of kinetic model. So that's interesting. So I'm going to finish now, which is reasonable. Just mentioning another very interesting finding of Jennifer, and I will finish on that, is that these iron oxidizing systems, here is the nitrate dependent BOFEN, is making a magnetite. So that could be a tracer of that. Again, one message is that this biomineralization of iron oxidizing system, which is related to the oxygen cycle, maybe in the minerals, if we go into the geological record, we can try to discuss the argumentation about reconstruction. Here, the fact of making magnetites is really very interesting because these magnetites, so iron 2, iron 3, you have initially only iron 2. By a complex mechanism, you make extracellularly, going through intermediate phases, you make extracellularly iron 2, iron 3 bearing phase. So this is one other rate, one other process you have to take into account. And the fact to make a magnetite is interesting. What is really surprising, and I have no clue about that, is that the magnetites are like in magnetotactic bacteria, they are single domain magnetites. So for instance, if you look for them in the environment, maybe you find single domain magnetites, you see maybe it's magnetotactic bacteria. Well, in that case, it's not, but that's not what is interesting here. What is interesting is in the magnetotactic bacteria, the common, and we have the presentations by Christopher and Nicolas, the explanation for having the single domain magnetite. So having a single domain magnetite, I'm sorry, I should explain that, is optimizing the magnetic moment for one given iron mass. So in the case of magnetic bacteria, it's understandable. They need to align, to use the permanent magnet to align. So one can imagine that evolution, there is selection pressure, and has made the system to go to this single domain magnetite, which are optimizing the magnetic moment. I have no clue in that case. That means that we know physico-chemical conditions, it's not very old, by the way, it's very recent, where we can make very nice chemically single domain magnetites. But it's very particular conditions. Why is it the case here? And so that's an interesting issue in looking at the mineralization traces of that iron oxidation system. And well, I just put the two images. I would like to put them without comment, right? You have the, I make a comment anyway. Yeah, you have the BOFEN making the magnetites, single domain. You have the magnetotactic bacteria making the magnetite, single domain. What is the relationship? So maybe Christopher would say they were all like that and some of them became like that. I don't know. Maybe one could say one day one like that could take use of these single domains and got an evolutionary advantage. I know that's a non-phylogenetic perspective on evolution. So, sorry. So I will finish. So I think what you should really understand is that it's not just words. Biomineralization is really a major actor of the geochemical cycles, and when we consider the global change now with the CO2 change and so on, biomineralization, we saw it for the corals, we see it for CO2 storage and so on, is really a major major actor. It's so that this field is very important for the understanding of the self-regulation of the planet, or self-deregulation sometimes. The biominerals contain a memory of geochemical cycles in the past. I did not push too much on that in my talk. This was this was in Anders' talk, but this is true, and especially the stable isotopes. I think if we can couple the mineralogy and the stable isotope in biomineralization mechanism, it's probably interesting. Of course, we are not naive. We know that we do not advocate a fully reductionist approach, which would start from your organism, the one you study, detailed mechanism, and go to the big picture. We know it's, but what maybe the interesting thing is that if each field is pushing things at the maximum, if there are some strong differences, then we can find things really very interesting. And again, I say discovery of new mechanisms, such as the intracellular biomineralization in cyanobacteria, for instance, it's really major. And finally, well, this is the consequence of that, right? So I thank you. I want to thank you all the collaborators. I showed a few of results I had, and okay, and for allowing me to doing that and giving me a paycheck at the end of this each month to doing that research, which is nice. And no, the LabEx Matisse really for making that possible. That's cool. I mean, it's a unique opportunity, and I think first I wrote great biomineralization short courses, and then I said, well, they will think my course is great. So but anyway. Thank you very much for this is a great thing.